Assalamualaikum, bismillahirrahmanirrahim. Hello everyone, hello my students. CHENG465 and PSI CHENG443. I always forget the second number, okay? For process chemical safety or process safety, industrial process safety course. And I'm sure by this moment you already have a good knowledge about process safety and chemical safety and how does fires and explosions do and how we can calculate those numbers, where we can identify how much fire or how much explosion and how can we overcome that. Of course, overcoming that to prevent them is more important than facing them. So we are trying to say here that overcoming things comes with preventing it at the beginning is much better than facing it later. So we are talking about safety. So we are trying to provide always inherent safety to our process. Of course, we need to understand what will happen so that we can deal with it. So continuing on, we already solved most of the problems of chapter 7. We are going to cover the last part of chapter 7, starting from 732. So 732 combines more than one idea from more than one chapter. So here it's talking about we are considering the installation of a storage vessel to hold 5,000 kilograms of liquid hydrogen. Okay, so we are talking about hydrogen as a liquid hydrogen, so it's like very volatile, and hydrogen just explodes with oxygen, right? So it's really dangerous. The hydrogen will be stored in an insulated vessel at 1 atmospheric absolute. That is like if you want to gauge pressure, 0 gauge pressure. So it's 1 atmospheric absolute pressure at its normal boiling point of 20 Kelvin. So imagine how that it's really low to keep that at liquid. Physical properties for liquid hydrogen at 20 Kelvin: density, heat capacity, heat of vaporization, and the molecular weight. So these are the information that we have for hydrogen. What we want to do, we wish to store the liquid hydrogen in a vertical cylinder storage tank with an inside diameter of 3 meters. A vapor volume equal to 10% of the liquid volume must be also included. So we are talking about we may add a vapor volume above that liquid volume. Okay, who signed me out? Okay, so a vapor volume equal to 10% of the liquid volume must also be included. What is the volume of the liquid and the tank in meter cube, and what height in meters is required? So we want to calculate the volume. Well, it's easy, right? Because if you want to calculate the volume, we have the density. Okay, we do have the density, and we have the mass that we want to store. So from mass and density, we can get the volume. And since it told us that it wants to add 10% for the vapor, so we'll add 10%, which is like multiplying it by 1.1 to get the total volume. So it's as simple as that for the first part. So let's start with the first part and do our problem here. So 732, 732. So what do we have? We have a mass of about 5,000 kilograms of hydrogen. And the density of hydrogen is 70.8 kilogram per meter cube. And so the volume will be what? Will be the 5,000 divided by 70.8, and that will be 70.6 meter cube. And of course, if you want the total volume, because it wants to add 10% over it, so we will say that 70.6 into 1.1, and that will be equal to 77.7 meter cube. So that's it for part A. I mean, part A was just like that, okay? So that was part A. So what about part B? Part B. In part B, it's asking us it's telling us that we have a 25 millimeter square 45. That means we have the inside the diameter and the outside outer diameter is connected to the bottom of the tank to drain the liquid hydrogen. Oh, I forgot one part here actually from part A. It says what height of the tank is required. Oh, what height is required? It's easy, okay? So just before going to part B, well, volume of the tank is pi r square h, right? So if you want the height, this is equal to volume over pi r square, and by that I'm going to divide pi r square. So volume is 77.7 over pi r square. R was 3, so diameter was 3, so radius is 2, so that will be like that. R square is equal to 11 meters. 11 meters. If I want the height of the liquid only without the vapor, I will say that is equal to 11 over 1.1, which is equal to 10 meters. Okay, and the height of the vapor will be left that for 1 meter. So that is for part A. So let's go now for part B. So this is what I have from the pipe connected to the bottom of the tank to drain the liquid hydrogen. If the pipe breaks off, that's a disaster. So the pipe breaks off, producing a hole with a diameter equal to the outer diameter of the pipe, because it is at the outer layer. What is the initial discharge of the liquid hydrogen, which is Qm, that is coming from the hole? Assume the liquid height is at full, so we have like full height. So this is what we have. So this is what we have from our system. It is full here, and that is the height, which is 10 meters. And we have a pipe here, and it happens that this pipe, what happens? It got broken. Okay, it got broken, and then what happens? Hydrogen is going out. Oh my god. So now with this hydrogen going out, what we are trying to calculate? We are trying to calculate here Qm. For this problem, if you can recall, if you go back to equation 412, so equation 412 for Qm is equal to rho into A into C naught, and that is multiplied by 2 GC PG, that is the gauge pressure, over rho plus GHL. Here in this case, the gauge pressure is 0 because we have 1 atmospheric pressure, so we are going to be left with 2 GHL only. So continuing the problem, that will be reduced to my equation, rho A C naught into 2 GHL. Okay, so that is my my equation now, and all I need to identify the rest of the values here. If you look at it, I think so we have most of our values. We already have the density. We need to calculate the area. That's simple. C naught for turbulent flow, you consider that as turbulent flow, hydrogen coming out. It's like it definitely be turbulent, causing a vapor cloud. So C naught would be like 0.61 in this case. And we have G and HL is already 10 meters. We calculated that. So we have HL is equal to 10 meters. If everything is meters, so G is 9.8 per meter per second square, and C naught is equal to 0.61. Okay, 0.61. So what else? I have the rho, which is already given to me, which is 70.8 kilogram per meter cube. And what I have here is just to calculate the area. And if you just want to do the calculation for the area, I'm going to do that in white. So area is equal to pi r square, or pi d square over 4, whatever you want to call that. So pi d square over 4, and here we are considering the outer diameter as it was said by the problem. So the outer diameter, if you recall, the outer diameter was 30.002 millimeter. So you need to divide this by 1000 for meter. So that will be 30.02 divided by 1000 square divided by 4, and that will be about 7.07 into 10 to the power minus 4 meters square. And if I have this, I just now need to do my substitution, and that is 70.8 multiplied by 7.07 into 10 to the power minus 4. Okay, and that is 2g into 9.8 into 10, and the answer will be 0.428 kilograms per second. So that is my QEM, that is the discharge rate. Actually, we also can calculate the time for all this to be discharged out. Okay, I did not ask here in this question to calculate the time, but we are saying that we can calculate the time for how much this whole hydrogen will be leaving my system. But that is not the problem now. So that was required by the problem. Let's go to part C. What distance from the storage will the 3 psi side overpressure? Okay, so it's telling us that there's a vapor cloud explosion, so or expecting that. So what distance in meter from the storage tank will the 3 psi overpressure occur in the event of an unconfined, of course it's unconfined because it went out of the vessel and it caused a vapor cloud explosion, and we are saying that it's taking the worst scenario that the whole 5,000 kilograms went outside. So considering that the whole went outside, which means I'm having the maximum explosion, and I want to know where is the overpressure of 3 psi. Why I want to measure, or why the question is trying to measure at 3 psi, because it says in table 6.9 that what damage would you expect based on the overpressure. If you have a 3 psi overpressure, what damage you would expect? You would expect damage not only to 50% destruction of brickwork of houses, but you would expect even heavy machines to be suffering. That means your whole plant will go out of service. So in heavy machines, industrial buildings suffer little damage. Okay. Steel frame buildings distort and pull away from foundation. So you're talking about buildings maybe falling off. Okay, it's going out of from its foundation. So that could be really serious. So we need to keep our buildings really far away. So now we are saying that how far should our buildings be? And this is why I said here that it wants to calculate the distance, what distance in meters to have the storage tank. Okay, so to do that, we need to calculate R, right? If you just recall from what we have taken from our last videos. So what we need is this R here, and this is part C, okay? So we need R, which is equal to the scale distance over the equivalent TNT mass. Okay, so this is what I need exactly. So if I need R, I need Z and MTNT. So I need two things here. To get Z, then I will need the overpressure, right? And I already have the overpressure. So and because I have the overpressure, what I need is the scaled pressure. Okay, so one by one. So what I'm trying to find out, Z, and to find out Z, since I have the P naught, okay, so I need the scaled pressure in this case, and this is calculated using what? Using P naught over PA, and I already have P naught over PA, so I have PS. Now, if I have PS, I will have my Z. That's good enough for this part. Now, what about the MTNT? MTNT, if you can recall, it is equal to this equation here, where we said MTNT into ETNT is equal to M to the energy of that compound here. So ETNT will be at the bottom here. So that is the equation that we are going to be using. So we need the delta heat of combustion for what? For hydrogen. And we need also the mass of hydrogen. This is this mu here, you're talking about 0.05 because it's unconfined. Okay, so we have the values actually. Here the value here is 0.05. The mass is already identified as 5,000 kilograms, right? And we have the delta heat of combustion is equal to, let me look at that, the heat of combustion is 241.8. You can get this from Appendix B, okay? Appendix B. So you can get that from Appendix B. Because this is kilojoules per mole, you need to work out your conversion here, where you say that we have about 18, hydrogen is out 2. So you have 2 grams per mole, okay? So 2 grams per mole, to put in kilograms, it will be like 0.002 kilograms per mole. Okay, so I'm just doing the conversion here. And what about the ETNT? We know that ETNT is 4,686 kilojoules per kilogram, which means that I'm going to get the answer in kilograms. Great. So I'm calculating here the MTNT, and in calculating, oops, sorry for that. So in calculating the MTNT, the MTNT is equal to 6,450 kilograms of equivalent TNT. Okay, so I calculated MTNT, and so that is done. So this is done. What about the Z? If we go back to our problem here, we need P naught over PA. So P naught, the overpressure over the ambient temperature, which is equal to 3 divided by 14.7, and that is equal to 0.2. So I'm talking about P naught of PS 0.2, and going to the figure 623, I'm going to find out that my Z value is going to be 9.2. So my Z value is going to be 9.2 meter per kilogram to the power third. And where did I get that from? Again, I got that from figure 623. Figure 623 for you to look at. Okay. Now I have everything. I'm just going to substitute. R is equal to Z, which is 9.2 into 6,450, and that is 171 meters. Okay, 171 meters. Okay, so this is the distance that keeps me safe keeps my building safe. I'll put in 200 meters, just considering that I have all that. Okay, great. So this is what I have. So what I need to do now, I need to go to part D, where it says that we need to develop a procedure to enter the vessel. So in service, we're talking about in service, right? We need to develop a procedure to enter the vessel prior to charging it with hydrogen. Before we put hydrogen, we have in service, put some vapor. To what target nitrogen concentration do we need to inert? So we want to know how much nitrogen I should put in to inert the vessel in order to prevent the formation of a flammable gas mixture when I'm filling the process. I'm putting it in service. So if you can remember that to put things in service, we had equations, and those equations that we had, I don't know if you can remember them. Let me show that to you. To have things in service, and we said that to have things in service, this was the figure that we had, and we said that these are the two equations that you can find here. Okay, so SiOC is equal to this, and we have another equation to calculate the inside service for the oxygen concentration. Okay, and of course, if I know the inside service for the oxygen concentration, which is at R, okay, so this is like point R, the point here, I will know what the 100% of nitrogen, okay, minus that the oxygen concentration, I will get how much nitrogen I need. Okay, so I'm going to get this point here, so just to know like how much I need of nitrogen. Okay, so I'm going to calculate using this method, and then I'm going to calculate using this method, and then experimentally from table 7.1, I'm going to find also the SiOC. Okay, so I'm going to calculate that using all green. So going back, if you go to table 7.1, you're going to find out that the SiOC is equal to 5.7% volume percent of oxygen, which means that if I subtract that, which is 100 minus 5.7, that will be 94.3% nitrogen. So this is what I need. I need to enter that with this amount before I fill in with hydrogen. Okay, what is the other method that I have? Well, I can go to the other method where I have SiOC is equal to Z into LFL divided by 1 minus LFL divided by 100. And in this case, I need the LFL values. If I get the LFL values, my LFL going to appendix B is equal to 4%. So you will get this from appendix B. Okay, LFL is equal to 4%, and so you just substitute. And this, oh, I need Z as well. Well, Z is easy because I know that H2 plus O2 gives me H2O. So that's my equation. And this is the Z here. So Z is half. We already know this equation. So we don't need to have a headache to know that is the balance of the equation. So this is 0.5 into LFL, which is 4 minus 1 minus 4 over 100. And the answer is going to be 2.08% of oxygen, which means that how much do I need from nitrogen? I need about 97.9%, something like that, if this 2.1. So that is 97.9% nitrogen. So this is the amount that I need. And of course, you already can see that I will always take it safe, and I will take the highest amount of nitrogen, because I can get the answer at by different ways. Now going through the third one, where the third equation, where I have the equation is equal to Z into LOC. Now I'm considering a different equation here, divided by Z minus LOC divided by 100. And here the LOC, if you go again to appendix B, you're going to find out that the LOC is equal to, for hydrogen, LOC for hydrogen, we're also talking about hydrogen, is equal to 5%. And here I'm going to multiply 0.5 into 5 divided by 0.5 minus 5 divided by 100, and that is 5.56% of oxygen. And again, that will contribute about to how much? If you subtract by 100, that is 94.4% nitrogen, which it seems very similar to the to the experimental one, and I would guess that would be like more accurate rather than using the LFLs only. Okay, so that was 732. That was the last part where we had identified the in-service of oxygen concentration for the in-service for the nitrogen concentration based on the in-service of oxygen concentration. Beautiful. That was a great problem that we have solved here, and that was for 732. Now we have finished 732. I'm going to keep 733. I mean, that's a simple to solve. And I think so finally we are going to solve a good problem here, which is 734 and 35 together. I'm going to consider 735 mainly in our to solve, but I need some information from 734. So let's read about it. Your plant is considering installing a 5,000 meter cube low pressure cone roof storage tank. So this is the low pressure of 5,000 meter cube that I want to install. The tank will store toluene. The plant is considering several options. The single tank within 10 meters of the process. So I have a single tank. Multiple small tanks within 10 meters of the process. This option requires 200 meters of additional piping. Of course, I will have a lot of additional piping and valves and maybe leaks. I will have even more possible probabilities because I'm having a lot of tanks and pipes. C, a single tank 100 meters from the process. This requires 150 meters of additional piping. Definitely, I'm using really one tank, but of course I will have one long pipe in this case. And or multiple smaller tanks 100 meters from the process. This requires 1,000 meters of additional piping plus additional valves. Okay, so here just considering that, well, I use a big tank or a small tank or many small tanks, and then the question is asking us consider each option and list the inherent safer feature with each. Select the single option that represents the most inherently safe design. Please make sure to provide support for your selection. What additional questions should you ask to improve the inherent safety of this process, of this installation. Now, considering the question here, I'm just going to, the calculations are all in 35, so I'm just going to explain the possibilities here. First, we have a lot of amount of toluene. That's a big amount of 5,000 meter cube. So why are we using this big amount here? So that's the first question here. We did not consider any inerting or something here. I mean, we need to consider this the values of LFL and LOC so that we can think of how much we need to inert this. All of these questions that comes to our mind. And then, do we need protection systems for that or not? Are there any static charges are going to be collected from that long pipe that I have for this big amount, and it comes at an end where it enters the end of this pipe, and so we really have some kind of grounding or bonding for the static charges. So you can hear how many questions do I have here. Now, considering there's some kind of a leak or something, 10 meters is very close. So forget about 10 meters. Whatever, single or multiple tanks, 10 meters too close, and it could cause a severe damage. However, 100 meters makes more sense for me, even though that this is a big amount. But talking about 100 meters, talking about 1,000 additional piping could be dangerous. Why? Because you have a lot of possibilities of having leakages, and so this could be a problem. However, talking about having a leak only in one pipe, that everything goes out, rather than having a leak only from one small tank, could mean that D would be safer. However, if these smaller tanks are close to each other, which means one explosion could explode all of them, it will mean that could be nonsense for D, and then C will be a better option. Okay, so that all depends on the arrangement, of course, of the tanks, and of course, going to the original questions: why do we need this much amount, and for what reason? So we need many questions to explain there. Now let's go to the real part that I will try to solve with you here. The real part here is saying that the plant asks you to consider the consequence of a tank explosion with resulting overpressure for options A and C. So what are options A and C? Single tank, or a single tank of 10 meters or 100 meters. Okay, and the second one has a 150 meter of additional piping. Okay, so a resulting overpressure for options A and C. For both cases, assume that the storage tank is drained of all liquid and contains only the saturation vapor pressure for liquid toluene at 25 degrees and 1 atmospheric total pressure with air. Okay, so what is the volume percentage of toluene in the vapor of each tank? So we need to calculate the volume percentage of toluene in the vapor for each tank in this sense. So that's the first part. Let's go to the other parts to get an overall view of the question. If the tank contains air, is the concentration flammable or not? So we need to consider that volume percentage with the lower flammability limit and the upper flammability limit. Is it within the flammability region or not? What is the stoichiometric concentration for toluene in air? We can do the balance. Is the vapor in the tank fuel rich or fuel lean, that it has a lot or less? Little, I mean. D, if an ignition explosion occurs within the storage tank, estimate the overpressure. So that means I need to see the scaled distance and the scaled pressure, and then I can calculate the amount, not the amount, I don't have the amount, I can calculate the P naught from the PS and PA that comes from the Z. Okay, so we can calculate based on the distance that I have, we can estimate the overpressure. Okay, which case is acceptable? Of course, one standing with a distance of R of 10 meters and the other with 100 meters. I would guess the one with the 100 meters could be the one which is acceptable, and we are going to discuss that later as well. What additional design features we recommend to reduce the probability of an explosion? Of course, inerting, we are going to discuss that to reduce that kind of an explosion. And we need, of course, the LFL and LOL values. And then we also may talk about the in-service, how to do the in-service as a part of to make how to fill in this with toluene. So this is the parts that we have here. It's very interesting question, and it's good to finish up with this question for this chapter. So 735. Okay, 735. So 735. Okay. So that is like 734 and 735 because we're using the equation from 734. So the first part of the question, I think so we already forgot. What is the volume percentage of toluene in the vapor of each tank? We can get the saturation vapor pressure. We already have the 25 degrees centigrade, and then we divide it by the 1 atmospheric pressure to get the volume percentage. So this is how it is done. So the first thing we need to do is to calculate the saturated vapor pressure. So that is part A, I would say. So length Psat is equal to the equation, the Antoine equation that you already know. Sorry for that. 16.0137 minus 3096.52. Okay, we need to put all the decimals because we are taking like these from the tables. And here the T is in Kelvin. Just consider that here's T is in Kelvin. So we already have the temperature, but I'm just telling you. If you go back, so you have to 25 degrees. So the 25 degrees, that means this will be 25 plus 273. Okay, I mean this is simple. I don't need to explain this. So Psat, after you calculate it, it will be 28.2 millimeter mercury, and of course we are going to divide this by the total pressure, which is 1 atmospheric pressure, that is 760 millimeter mercury. We'll get the volume percentage. Okay, the volume percentage which will be 3.71%. Now the volume percentage is equal to 3.71%. Going to part B, we need that information because it's telling us if the tank contains air, is this concentration flammable or not. So going for appendix B, we are going to find that the LFL is equal to 1.2% and the upper flammability limit is 7.1%. And you directly can realize that my 3.71%, it just sits between them, which means that it is flammable. Okay, it means that it is flammable. Okay, my God, it is flammable. So now let's go to C. What is the stoichiometric concentration for toluene in air? Is the vapor lean or not? So going to the stoichiometric concentration, that means you need to do the balancing part, and the balancing part, that means toluene, which is C7H8 plus some kind of O2, like you need to do the balance. Okay, CO2 plus H2O. And the first thing I said that when you do the balancing, you go to the H. So you have 8H here. So you need to multiply by 4 to make 8. And then you go to the carbon. I need 7 carbons. So I put 7 carbons here. So that's 7 carbons. Now go back to the oxygen. I have 14 plus 18. So I have 18 oxygen. So I need to multiply 9 multiplied by 2 to be 18. Okay, great. So that is the balance. And now I already found out that the Z value here, the Z value is equal to 9, and now to do my stoichiometric concentration, the CST, if you can recall, which is equal to 100 divided by Z over 0.21, and that will be 100 over 1 plus 9 over 0.21, which is equal to 2.28%. Now, if you go and read about it, like where we can identify that it is rich or not, usually the concentration of 3.34% of toluene is fuel rich. Well, it's not only for toluene, but if you have this kind of percentage of 3.34%, you can say that is fuel rich. What do we have is 2.28 here actually. So we can consider that. Just to fix that, we didn't have 3.34. Actually, what we had here from the concentration that you obtained the volume percent was 3.71%, right? So now this the 3.71% is fuel rich. Why? Because it's greater than the CST, which is the 2.28%. Okay, so that is how we know that it is rich or not. Let's go to D to just make it more practical. If an ignition and explosion occurs with a storage tank, estimate the overpressure at the process boundary for each case. Now we have two cases, right? So if an ignition occurs, estimate the overpressure, and actually we want to discuss if this is acceptable with one with 10 meters and the other with 100 meters. So going to part C. So let's do part C. Now, is it part C or part D? Okay, part D, sorry. Okay, so that is part D. So what do we have here? We have like the one with the 10 meters and the other is the 100 meters. So let's start solving the problem, but we need to organize how we are going to solve this problem. So what we need here is actually is to calculate the P naught, right? The overpressure. So if you need P naught, and of course we know that we can get P naught if we have we already have the ambient temperature, but we need the scaled the PS, and to get the to know what P naught scale distance, we need the Z, right? And what the Z is equal to? Z is equal to the R over MTNT to the power third, which means that I need also that information. Now starting, I don't have MTNT. I need to calculate MTNT, but I have R, which is 100 meter or 10 meters, right? So we are going to calculate this, and the MTNT, actually, if you can recall, what is the equation for MTNT? It is equal to the nu into the mass into the delta heat of combustion over ETNT. So that is the equation. And do we have the mass here or not? If you go back, yes, I do have the mass. Let me see here, because I have two problems here. So I have the tank store, is installing 5,000 meter cube. So using the density and I have the volume, I can find the mass, and now I already have the mass, so I can find the mass here. And the delta heat of combustion, I can get that from appendix B. And ETNT, I already have ETNT. Now this is happening in a closed vessel, so I'm going to consider nu is equal to 1. Okay, so now I need to calculate the mass. I already have that and have that. Okay, so let's put the numbers. So this is 4686. Let me put that in blue just to make them different. So this is 4686 kilojoules per kilogram, and my delta heat of combustion, that comes from appendix B, which is 40,800 and 586 kilojoules per kilogram. Okay, so this is what I have here. And what about the mass here? Of course, we need to get the mass where we said that we can get the mass from the total volume. Well, the total volume is 5,000 meter cube. Okay, 5,000 meter cube. And actually, if you think of it, was it 5,000 meter cube? Yes, it is 5,000 meter cube. And do I have the volume percentage of that? I have the volume percentage of that. But I have the toluene is only 3.71%. So I can get a good guess, an idea of this 3.71% of toluene by multiplying it by 5,000 to get a good idea about it. Or we could say that we could use the PV is equal to nRT, and I can get the volume from the PV is equal to nRT term, and I can multiply this also by the percentage. I can get the density from the PV is equal to nRT term, where I can get the answer from there as well. So whatever you want to do, I'm going to just say that is multiplied by 3.71%. which is about equal to, let me multiply this, it's about 7,000 or 6,000. Let me do this quickly. So this is 3.71 multiplied by 5,000. So that is the amount that I have. But actually, if I multiply this, I'm not getting the mass. I'm just getting what? I'm getting the volume only. Okay, sorry for that. So I'm getting the volume. So what I need to multiply, I still need to multiply by the density here, the density. And actually, what is the density equal to? You go and calculate back the density, which you know that density is equal to PM over RT from this equation here. And you're going to find that this is equal to 3.76 kilograms per meter cube. Okay, great. So we calculated the density, we multiplied the density by 3.71%, multiplied by 5,000 to get the mass. Here we have the nu is equal to 1. We have the delta F of combustion, we have ET and T. We do our calculation to find out what? To find the MTNT, okay? To find the MTNT. And the MTNT is going to be equal to 6,037 kilograms, okay, of TNT. So now we found that this is 6,037 kilograms. What about the R? R, we already have the two cases of 110. So let's calculate for the 100 case. Okay, so for the 100 meter case, my Z will be equal to R over MTNT to the power third, and this is equal to 100 meters divided by 6,037 to the power third. What happened to my handwriting? Is equal to 5.49. And of course, from figure 623, we are going to find out by knowing, of course, P naught, right? The PS is equal to 0.4, and then we are going to calculate P naught, where P naught is equal to PS multiplied by PA, which is equal to 0.4 atmospheric pressure, and that is equal to 5.9 psi. 5.9 psi. And if you go to the tables, you can see how much damage that will cause. Now, considering, now imagine, like this is like 5.9 psi. I know if you go to that table here, 5.9 psi over pressure, imagine like how much it would cause. It would cause about 6, which is 5 to 7, nearly complete destruction of houses. Do you see this? Complete destruction of houses. So that is not, that is really a big amount. It will cause a lot of destruction. Well, now imagine what we are going to find. We are going to find now the 10 meter case. The 10 meter case. And the 10 meter case, we are going to calculate the Z value again. And Z is equal to 10 over 6,037 kilograms to the power third. And this will be equal to 0.55. And from the figure from figure 623, we are going to find out that the P naught value, the PS value is equal to, I'm just looking at the PS value here, seconds. So my PS value, which is 70 atmospheric, oh my god. So you're talking about P naught of 70, because P naught is like, you're just multiplying by the ambient temperature, right? You're multiplying PS with PA, so that is 70. I can't imagine that. How many PSI you're talking about? 1,029 PSI. Is this crazy? And that's why I told you that, but 10 meter case, you're killing. You're killing. I mean, you're talking about 10, and then if it just jumps to 300, saying that like 10 is like probable total destruction of everything, of everything, badly damaged, very heavy machines, like, and he cannot think of even more than that. So what about 70? I mean, that is killing. That is killing. So that is a total destruction, huge destruction of the whole plant. Okay, so that is like a destruction of a whole plant. So we need to be careful of what numbers we just think of and of storing, and definitely for part F, when it's asking us what do we need to do a lot of jobs like inerting, bonding, and grounding. And of course bonding and grounding is because of the static charges here, but inerting, definitely we need a lot of inerting there. Great, so that was the problem of 735, and that is the end of solving of the problems here. There are more problems if you would like to solve. I would advise, if you'd like to solve, you can solve problem 36 and 37. So if you would like to solve, you can solve problem 36 and 37. They are very related and they are good also. Until then, thank you very much. That was the end of our session for solving chapter 6, and let's make a rainbow here and be happy that we had done a good job here, and all the best for all of you, and wish you a very happy smile in your life, and believe me, that depends on your heart and your goals in your life and your mission that you have. Make yourself dedicated to it. Will create this smile that will never stop. That will never stop. Believe me, it all depends on you. Thank you very much. All the best. This is Dr. Bassam Al-Hamad. Ma'assalam.